Welcome to Physics Pathfinder. You are watching the part 2 of rigid body mechanics. In this section, we'll be solving the exam style questions on rotational motion. Let's see our first example. A solid cylinder of mass m and radius r is free to rotate about a horizontal axle. A rope is tied to the cylinder and the mass of the cylinder is m/4 is attached to the end of the rope. Initially, the mass is at rest. Later, the block is released. Moment of inertia for this system is given as half mr. What are you required to prove? You're required to show the answer for alpha is g over 3r. So if you go back to the question and see when the mass is moving, net force, linear force is ma, while rotational force is I alpha. Let's use what we know. Solve it here, the side, so that we can see the question as well. So if you can see, force acting upwards is the tension. The force acting downwards is the weight. The net force is ma. So since the motion is downwards, weight is positive. So we can write mg over 4 minus the tension is equal to the net force, which is the mass m over 4, the linear acceleration a. Now we'll talk about the rotational forces. For the rotational force, if T is the force acting, then the distance perpendicular to that is the radius. That is equal to I alpha. I is already given to you for this mass, which is half mr square. It's alpha. You need to get the value of alpha, substituting the value of T from the previous equation. So from this equation, we can see T is nothing but mg by 4 minus a multiply r to both these terms. Get mgr by 4 minus mar by 4. Left hand side is done. Right hand side is of r square. Go back to what has to be derived. There is no a in this equation. You have to get the value of alpha in terms of g and 3r. We can get rid of this a. You can see over 2 over 4. Yes. A is alpha r. So instead of a, put an alpha and also multiply it with one more r, this becomes r square over 4 is equal to half r square. Now just rearranging the alpha terms together, cancelling the common multiple, get the answer, which is required. Answer is alpha is equal to G over 3R. What you see is the marking scheme given in the paper. Steps are given, which we have solved here. So you get 1 mark each for each of these steps. Then the final answer is the last mark. Final answer is alpha is G over 3R. So here you have to make a note that rotational acceleration is G over R. Let's move further. Prove that the tension on the string is mg over 6. So if you remember, we can use one of these equations. ER is half mr square alpha. We already know the value of alpha. Let's substitute it there. ER is equal to half m r square. Just now got the value of alpha as g over 3r. G over cancel this r and r. This r and this r. We're left with what has to be derived, mg over 6. This is what we had to prove. Tension is mg over 6. Next is, if the block falls through a distance of 0.5 meters before hitting the ground, show that t is 0.55 seconds after release. Here we can use the equations of motion. S is equal to t plus 1/2 at square. S is given to you. You have to prove t is 0.55 seconds. So let's substitute it. 0.5. Block is released from rest. You have seen the question, initial part. This is 0 plus 1/2. Now, if you go back to the what we have derived, alpha is G over 3R. A is equal to R alpha. Alpha is A over R. You can compare these two equations, A over R and G over 3R. You can very well see that A, acceleration in this case, is G over 3. Substituting acceleration here, G over 3 times t square. Taking t as the subject, rearrange, is equal to 0.5 times 6 per g. Square root of that should give you an answer rounded off to what is required. 548 something, so which can be rounded off to seconds. Let's take it further now. Use the data. R is 0.2 meters, mass is 12 kg. Calculate for the cylinder the angular momentum. Remember the formula of angular momentum. L is equal to moment of inertia times omega, angular velocity. You see, we know moment of inertia, but we don't know omega. Start with finding omega. P is equal to R omega. Omega is V over R. No idea of R also. We have to work out V first. No idea of V, I meant. So we can start with V is equal to U plus AT. U is 0. A was G over 3. E was 0.55. Using this, you can find velocity. Velocity, what we get is 1.83. Velocity is around 1.83. This velocity over R, which is given in the question as 0.2, 0.83 over 0.2, which is around 9.166, that is 917 is omega. Now let's go back to L of M times R square, which is 0.2 square. This is I times 9.17 should give you 0.2, which is the answer. The answer is 2.2 joules second or radians per second. Radians per second or joules per second. Okay. Next part, kinetic energy. Formula of kinetic energy. Kinetic energy is half I omega square. You need not to recalculate omega. You already have omega. Same omega here. It's half 2 square omega square, which is 9.17 square. As we do this, we get the expected answer in joules. See here the solution, which is 9.7 joules. Let's take it further. Let's now understand the ladder problem. There is a ladder that is resting on the wall and it is at an angle of theta with respect to ground. Let's now analyze the forces acting on such a ladder. Forces acting on the ladder are, first, if this is the wall, there is a normal force perpendicular to the wall. There is a normal force perpendicular to the floor. There is a frictional force which goes against the motion. This is the angle theta. At the center of mass, you have the weight that is pointing downwards. Now we'll resolve them into different components. If you can see here, this is the component of force perpendicular the normal. So this force has to be perpendicular to the length of the ladder. So if you can see here, this is the length of the ladder be given in the question. Length of the ladder would be some meters. So this normal force and the perpendicular distance is the length of the ladder. If we see the weight, the other rotational force, the other part of the rotational force is, this is the weight. The perpendicular component is the cos theta component. This force is at a distance of half the length of the ladder, which is this. Using these concepts, let's understand. And if the ladder isn't moving, we can also tell that forces are balanced. That is, the torque is balanced and the linear forces are balanced. Let's see a situation as you see in this question. There is a ladder which is 50 Newton in weight. The length of the ladder is given to you as 4 meters. It is at an angle of 60 with respect to ground. Outline Y, the normal force acting on the ladder at the point of contact with the wall. Something like this is equal to the frictional force, which is this. Very clearly, to achieve equilibrium, the linear forces has to be balanced. Because of that reason, you can tell that the normal force is equal to the frictional force. Since it's only 1 mark, we need to just write about translational equilibrium. Calculate this frictional force. Frictional force. So if you can see here, we'll go back to the diagram that we had the previous. You can see here the weight is acting downwards. Component perpendicular to the weight is here. This is F theta, the adjacent part weight, the part which is perpendicular to the wall. This was another. You are taking a component of normal force which is perpendicular to the ladder. As per the torque equation, normal force sine theta of that, the force perpendicular to the ladder. Now, for equilibrium, the forces are balanced. So we can very well tell that the force of friction is equal to the normal force. This is for linear. For rotational motion, we can tell that Fn is the force times the distance to the pivot is the whole length of the ladder, which is the distance of the force from the pivot is 4 meters. So this times sine of 60 is corrected again. As per the linear force we had, the force of friction is equal to the normal force. As per the rotational force, we have Fn is the normal force times sine of 60 times the length of the ladder, which is 4 meters, is equal to the component of weight, which is G, which is 50 Newton, cos of 60 times the distance is this, which is exactly from the center to this point, which is half the length, which is 2 meters. This mg is given to be 50 Newton. From the above equation, we know Fn is the force of friction. So rearranging, get force of friction is equal to, instead of mg, it is 50 plus 60 times 2 per sine 60 times 4. Rearranging, you get the answer that is expected. It's calculated. We get the answer, which is around 14.4 newtons. Now, if the coefficient of friction is given, you have to calculate whether the ladder is going to slip or not. Know that force of friction is also equal to mu times all force, which is mu times mg, which is 0.4, mg was 50. This is around 20 newtons. Force of friction, what we got is 14.4, and here the answer is 20. So naturally, maximum force required is 20, and we are having it lesser than that, hence it won't slip. Last part of today's example, given a moment of inertia, you have to find the total kinetic energy. So basically, the total kinetic energy has two parts: kinetic energy linear and kinetic energy rotational. Just plain calculated, you get the total kinetic energy. Let's see. Kinetic energy linear is half mv square, while kinetic energy rotational is half I, which is given in the question, which is over 5 square omega square. And V is our omega, so omega is square over r square. Very clearly cancel these r square. So the 2. Now only the LCM is left. If you take the LCM, you get 7/10 square. So folks, that's all for today. Like and subscribe the channel. Press the bell button to get the regular reminders.